So, I want to talk about exponential and logarithmic functions because I just think they're really cool and amazing. So starting with exponential functions, they take the form of y equals some base constant raised to the x. The example of this I like to give is Moore's law, which says that the density of transistors that we're able to build doubles every so many, doubles every decade. I don't know if that's the right figure, whatever. In this case, our base constant is 2 because we're doubling, and then x is the number of decades. So the density of transistors is growing exponentially with decades. A nice feature of the exponential function is that if you plot its vertical axis logarithmically, you linearize it, and that can give you a greater resolution of how it behaves over a range of values. Now, a second nice feature of the exponential function is that it is consistent in shape everywhere along the curve. An example I prepared of this is an exponential curve from exponential values from 0 to 100, and I cut that distribution into thirds, overlap them on top of each other, and then normalize their amplitudes, and you see this other curve going from 0 to 33 of all three of these portions of the other curve having exactly the same shape. Now, a logarithmic function is exactly the same as the exponential function, only you're flipping your x and y. So when you switch your x and y and then you solve for y, you get the definition of the logarithmic function. When I say log base b of x equals y, that's exactly the same as saying b raised to some value y is equal to x. That's the definition of the logarithmic function. And as I show here, the exponential function and the logarithmic function are mirrored of each other across this dotted line. So they can be used to describe the same things, just depending on what you want your x and what you want your y to be. It's the same function or distribution. Now, there are a lot of things in nature that follow exponential or logarithmic distributions. For example, light intensity. If you're walking around in the dark, then your eyes are able to detect slight gradients of shadows in order to find your way around. Whereas in the light of day, you're not as sensitive to those dark shadows, and you can only detect larger gradients of light because you have so much more light to work with. So your optical sensitivity to light intensity is following an exponential curve. Very, very sensitive when you have very little light, not very sensitive when you have a whole lot of light. Same thing with sound intensity. What sound is the difference between high pressure and the low pressure portions of a sound wave. And we can detect fairly quiet sounds of rustling of leaves, and we can process louder sounds, but we can't process slight nuances between louder sounds as we can between quieter sounds. So the way that we describe noise is logarithmically. Decibel is defined as 20 times the log of the pressure difference. I don't know where the 20 comes from. That just makes no sense to me. Now, another example also with sound is frequency. The note A on one octave is double the note A on the next octave and on the next octave, and we hear all these as the same note even though they're of different frequencies. And we hear them as the same note because they are doublings of the frequency. So the way that we hear sound and frequency is exponential. And another example, and this is the one that really bends my mind, is if we consider the distribution of the lengths of rivers. Consider counting the number of rivers that are under 10 miles long. And then add to that the number of rivers that are 20 miles long. You're adding an appreciable number of rivers. But then when you add the number of rivers that are under 30 miles long, you're not adding as many rivers because the number of rivers tends more towards the shorter length. But there's also no real bounds on the upper limited length of a river. There is a limit, but the number of rivers that are really, really long are diminishing in numbers. So the cumulative distribution of the number of rivers actually follows a logarithmic distribution, which, okay, that's reasonable. Now, when you look at the distribution of rivers, not the cumulative, but the actual distribution, you take the derivative of the cumulative and you get basically 1 over x is the distribution for the number of rivers. And the same goes for the populations of cities or any other kind of distribution that you can think of that tends to have more examples at the lower end of the distribution, but no real hard set limit at the upper end of the distribution, just vanishingly fewer examples. Where this gets really trippy is when I look at the number of rivers that have a length measurement starting with the digit 1, either from 0 to 1 miles, or from 10 to 20 miles, or from 100 to 200 miles. All of these start with the digit 1. And I can compare the number of rivers that start with that digit to the number of rivers that start with the number 2 or the number 3. And it's consistent from one decade to the next. And I can actually plot the number of rivers that start with the digit 1, 2, 3, 4, and 5 following this distribution. And since this distribution follows from the integral of different portions under this 1 over x distribution, it comes out to being a logarithmic curve. I'll plot the logarithmic form on there. And this is known as Benford's law. And just the existence of Benford's law kind of warps my mind a little bit, because it doesn't so much matter what you're talking about, and it doesn't matter what units you're using, whether miles or kilometers or feet. And where it gets really trippy is that it shows up in accounting. Benford's law is used to detect accounting fraud. If you look at an individual accountant's numbers and you tabulate all of their figures that start with the number 1, 2, 3, or 4, or 5, whether that's hundreds of dollars, thousands of dollars, tens of dollars, and you tally it all up, if it does not follow this distribution, that's a really good indicator of accounting fraud. So if you start looking at human perceptions of numbers, you might expect to see a logarithmic perception. And indeed, we do see that distribution. If you were to interview someone who doesn't have a standard mathematical training and show them a pile of 9 marbles and 1 marble and ask them to place other quantities of marbles between these two quantities based on where they think it should belong, they will place 3 marbles right between the 9 and the 1, because 3 marbles is logarithmically the center between 1 and 9. And our sensitivity then between the quantities of marbles diminishes as we go up in the number of marbles. The difference between 8 marbles and 9 marbles is much smaller than the difference between 1 marble and 2 marbles, which makes sense because it's a much smaller percent change. So the way we think about numbers intuitively has been demonstrated to be logarithmic, as we should expect it to be. Another example of this is loss aversion bias. And loss aversion bias is often described as a logical fallacy. And sometimes it is, I'll come back to that. But very often, what we're calling a loss aversion bias is not a logical fallacy. We're saying that when people are presented with the equal chances of winning $10 or losing $10, they will not take the risk, even though the probability and the gains and losses altogether are net zero. So there's no reason why they should not take the losses. But if you consider someone who has $100, then the prospect of gaining $10 is not a 10% gain per se. It's a 0.95% change from 100 to 110. Whereas the loss from $100 to $90 is not exactly a 10% loss, it is a 10.5% change. So the relevant factor that we're thinking of is the logarithmic factor, which is our percent change. A 9.5% profit does not offset a 10.5% risk. And this is the logarithmic thinking that drives loss aversion bias. Now, I should admit that this thinking process is strictly intuitive, and sometimes the numbers will in fact favor taking the risk, and both people and Capuchins will not favor taking the risk. My point being here that logarithmic and exponential functions are really cool in that they show up all over nature, in our perception of nature, in our thinking, and in constructs such as economy and accounting.